This is section 6.1, day 3, the last day of this section, and we just have a couple things to wrap up here, some applications of this radian measure. It says here the radian measure formula, theta equals S divided by R. That was from the previous section. Can be used to measure the arc length along a circle. If we take this equation and we multiply both sides by the quantity R, we're going to multiply by R on both sides. So we're going to get S is equal to R times theta. So for a circle of radius R, a central angle theta intercepts an arc of length S given by S equals R times theta, where theta is measured in radians. That's critical. This formula only works when our angle measure is in radians. Now let's step back and just look at the picture here. I think graphically this might be easier to see. S equals R times theta. So here's S. S is this arc length. It's a piece of the circumference of the circle. That's S. R is our radius, of course, and theta is our angle. So if I want to know the length of this chunk of the circumference of the circle, this arc length, denoted by the variable S, if I want to know how long S is, I just take the radius and multiply it by the angle. But here there's a little catch. This angle is given to us in degrees. So to find the length of this arc, to find the length of S, we have to convert this angle to radian measure. Once we do that, we just multiply it by the radius, and we're done. So to solve the example 6 here, we want to find the arc length S. First, I want to take my angle, 240 degrees, and I'm going to convert that to radian measure. And remember, we multiply by pi radians over 180 degrees. The degrees cancel. We multiply straight across and get 240 pi radians divided by 180. When we divide that out, we get 4/3 pi, or 4 pi over 3. So this angle here is 240 degrees, and it is also in radian measure 4/3 pi. So now that we've converted the angle into radian measure, we just multiply by the radius that we have. Here in this formula is S equals R times theta. Well, we're trying to find S. We know our radius from the picture is 4. And now we have our angle in radian measure, 4/3 pi. And we multiply straight across. 16 pi divided by 3. And if we punch that into the calculator, we're going to get 16 approximately 16.76. I think the book example was using feet as their unit. So that's how simple it is. Convert your angle into radians if you need to. Multiply the radian measure of the angle times the radius to get the arc length. Another thing we can look at along these lines is linear speed and angular speed. Consider a particle moving at a constant speed along a circular arc of radius r. If S is the length of the arc traveled in time t, then the linear speed v is the variable we're going to use for linear speed, the linear speed of that particle is arc length over time, or S divided by t. And I like to even think, look back, this S was equal to R times theta. So instead of putting an S up here, you could put R times theta divided by time. And that'll give us the linear speed of a particle or another object. Moreover, if theta is an angle in radian measure corresponding to arc length S, then the angular speed, this is omega, the lowercase Greek letter omega, the angular speed of the particle is, you just take your angle, theta, and divide it by time. And that'll show you how fast your angle is changing. Here, if we look example 7, finding linear speed, we're looking at a clock. And it says the second hand of the clock is 10.2 centimeters long, as shown in the figure. Find the linear speed of the tip of the second hand as it passes around the clock face. So here at the very tip of the second hand, we're considering that sort of like a particle, and we want to know how fast it is moving around the face of that clock. So to find the linear speed of the tip of this second hand, If we jump back here, we know our linear speed is v, and that is equal to s divided by t, or r theta over t. So v equals r theta divided by time. So to start plugging stuff into the formula here, the radius is the easiest thing to find. It's given right in the picture. The radius of that second hand is 10.2 centimeters. And the angle, we want to go a pass around the clock face. So the tip of this is going to go all the way around the clock. In radian measure, that's 2 pi. So our angle is 2 pi, a full revolution. And here we're talking about the second hand going around the clock. How long does that take? Well, it takes 60 seconds. So if we multiply straight across, we get 20.4 pi divided by 60. And if we punch that into our calculator and round, we get approximately 1.068 centimeters per second. Our units in the numerator were centimeters. Our denominator was in seconds. So it's numerator as denominator, or centimeters per second. Here in example 8, we have a windmill. And now we're going to find an angular and the linear speed. So the blades of a wind turbine are 116 feet long. The propeller rotates 15 revolutions per minute. In part A, we're going to find the angular speed in radians per minute. In part B, we're going to find the linear speed of the tip of the blade, much like we did in the previous example. So for part A, to find the angular speed. Angular speed is theta divided by time. And if we look here, we know that 1 revolution of the windmill blades is 2 pi radians. And we want to find radians per minute. Well, how many rotations does the blade make per minute? It makes 15 RPMs given in the problem. So we take our 2 pi, which is 1 revolution, and multiply that by 15, and we get 30 pi. 30 pi radians per minute. You know, here as this blade rotates around, if I sort of draw an XY axis in here, you know, this is rotating around, I'll assume counterclockwise. In 1 minute, it does 30 pi radians. This angle is changing every minute. It changes at 30 pi. For part B. Part B says find the linear tip, or the linear speed of the tip of the blade. And that's a lot like we did in the last example. That is V is equal to R theta over T. V is equal to R theta divided by time. Well, now here our radius is 116 feet. Our theta, our angle that as this occurs, is we found in part A, 30 pi radians. So 30 pi radians, and all divided by time is, we'll just go per minute. Per minute divided by 1. So if we multiply straight across and ignore the denominator of 1, we get 10,933 feet per minute. That's the end of this section. Here are 3 practice problems. Pause the video, try these out, turn the video back on, and see how you did. The first one is a slight twist. We know that S is equal to R times theta. In the previous examples, we were given the radius and an angle, so we found S. And remember, S is arc length. In this problem, we are given arc length, and we have the radius. So what we're trying to find is the angle in radians. We want to know how much this angle is. Well, S equals R times theta. We have 2 of the 3. We know that S is 32. We know the radius is 7, and we're solving for theta. So here we're going to divide both sides by 7. And we get theta equals 32/7. And if we want to convert that into a decimal, we divide. And we get approximately 4.57 radians. Now notice our measure does not have a pi in it. If we wanted to, we could take 4.57 radians and divide it by 3.14. And we would have our decimal answer, and there would be a pi in our final answer for radian measure. But let's just leave this one as a simple number. Number 91 is exactly like 87. 87 was given to you graphically. Here is your S, your arc length. Here's the radius. In this one, this is your radius. This is your arc length. It's in your notes, but it's not here in my slideshow. We're just going to set it up exactly like we did the one above it. S is equal to R times theta. So now here our radius is 14.5. And that is equal to the arc length of 25 centimeters. So now we're going to divide both sides by 14.5. That'll divide out, and then theta will equal 25 divided by 14.5 on your calculator is 1.72 radians. The very last one here is a lot like the first example from the very first slide. So let me move some of this out of the way. So if we read the directions, it says find the arc length on a circle of radius r intercepted by central angle theta. But now look here, theta is given in degrees and not radians. We want S is equal to R times theta. So we have the radius. The radius is 3 meters. We are looking for S. Theta we have in degrees, but remember we do not want to put a degree measured angle in this formula. So we want to take 30 degrees and we want to convert to radians. So we're going to multiply by our fraction with degrees in the bottom, radians in the numerator. Degrees cancel. We multiply across and get 30 pi radians divided by 180. And then this reduces down. 3 over 18 divided by 3, we get 1/6 pi over 6. That is the measure we want to put in for theta. 3 times pi over 6. And if we multiply straight across, we get 3 pi over 6. And the 3/6 reduces down to a half pi. So it said find the length of the arc on a circle of radius r intercepted by angle theta. So we have pi over 2, or 3.14 divided by 2 is going to be, ooh, I don't have my calculator here. Let's do this, calculator. 3.14 divided by 2, 3.14 divided by 2 is 1.57. So approximately 1.57, and our units here were meters. So if we think about this visually, we had a circle. We knew that the radius was 3 meters, and we had a 30-degree angle. 30-degree angle is pretty small. We converted that into radian measure, and we're saying that this arc length, this chunk of the circumference of this circle, is approximately 1.57 meters.